Hello and welcome to today's video. In this video we're going to talk about applications of L'Hopital's rule, and we're going to see more examples of how to apply it, specifically in situations that are not yet conformant to the rule 0 over 0 or infinity over infinity, but that can be reformulated in such a way. And this is going to be the focus of today's video. So the title is L'Hopital's rule examples. And as the title suggests, this consists of just examples. So we start with an example of a limit of a type infinity minus infinity. Now it's worth mentioning that not all limits of that type may be computed using L'Hopital's rule. Not all limits of that type may be computed using the method that I'm going to show you. But it's always worth having in mind that L'Hopital's rule might be applicable if you reformulate that in a proper way. And I'm going to show you examples of how to do that so that you know how to treat limits like that, possibly. So the example is the following. We're looking at a limit of x as x tends to 1 from above of the expression x over x minus 1 minus 1 over e to the power of x minus 1 minus 1. What you'll surely notice is that as x tends to 1, this here tends to 1, this here tends to 0. So this whole fraction here tends to infinity. X tends to 1 from above, so it's going to be plus infinity because that x minus 1 is always positive, as x is always greater than 1. In this example here, on the right, as x tends to 1, this exponent here tends to 0, so e to the power of 0, that surely tends to 1, and that means that whole denominator tends to 0, so what we get is again plus infinity here. Now we have a limit of the type infinity minus infinity. Now we can try to reformulate that in a way that L'Hopital's rule can be applied. And in this case, this is particularly easy. All you have to do is compute the common denominator of those two fractions here and then write this here as one large fraction. And it will turn out that's basically all you have to do. So if you do this, this turns into the limit as x tends to 1 from above. The common denominator is, of course, simply x minus 1 times e to the x minus 1 minus 1. So just the product of those two. And then we have to multiply this by this. So we get x times e to the x minus 1 minus 1. And we have to multiply this by this. So we get minus x minus 1. And if you look at that, you can see now that as x tends to 1, this expression tends to 0. E tends to e to the power of 0, so to 1. And that means this expression tends to 0. And of course, that here tends to 1. So the whole numerator tends to 0. And here, x minus 1 tends to 0, and same thing here. This here tends to 1, so this whole expression tends to 0. So again, we get a denominator that tends to 0. And that means we now have a limit of the type 0 divided by 0. We have differentiable functions, so we can try to apply L'Hopital's rule. And we do that by taking the derivatives. That's a little work here. Here there's a product of two functions, so we have to apply product rule to compute the derivative here. We start by differentiating x, so we are left with a to the x minus 1 minus 1. And then we differentiate this expression here So this is x times, and the derivative here is e to the power of x minus 1. Chain rule applied to that, just use a factor of 1, so nothing to add here. And this minus 1 vanishes. And then we have to differentiate that. That in turn is easy. It's just minus x plus 1 differentiated. So we're left with minus 1. So that was easy. For the denominator, we basically have to do similar things here. Again, we have a product of two functions, so we apply product rule. We start by differentiating that factor, and that factor differentiated is just 1. So we're left with e to the x minus 1 minus 1 plus, and now we differentiate this factor here, and we've done that already. So this is x minus 1 times e to the x minus 1. And what happens? Well, as you can see, again, this whole expression here tends to 0. E to the power of 0 is 1. X tends to 1, so this factor here tends to 1. And that means 0 plus 1 minus 1. So the numerator again tends to 0. And for the denominator, this expression tends to 0. This here tends to 1. And this factor tends to 0. So also the denominator tends to 0. And we're again in a situation where we can apply L'Hopital's rule. So it's not uncommon to apply that rule multiple times. So let's try that. And we obtain the limit as x tends to 1 from above. Differentiating that, we've done that already. That is e to the power of x minus 1. The minus 1 vanishes. Here we need product rule once again. So that is plus e to the x minus 1 plus x e to the x minus 1. Minus 1 just vanishes. And for the denominator, we've done this here multiple times by now. So the derivative of that expression is e to the x minus 1. And again, here we need product rule. So that derivative is e to the x minus 1 plus x minus 1 e to the x minus 1. And now let's see about the limits here. So this here goes to 1. This here tends to 1. And this here tends to 1 times 1, so also to 1. So we're left that 0 situation. This tends to 1. This tends to 1. This here still tends to 0 because x minus 1 tends to 0. But that means we have a constant value in the numerator and in the denominator in the limit. So the limit will just be 3 over 2. And that's how you compute limits of that type using L'Hopital's rule. Now, for another example, and another very common type is the one where you have a product, say, of the form 0 times infinity or minus infinity. A common example for that is the limit as x tends to 0 of x times the logarithm of x. And as you know, the logarithm tends to minus infinity for x to 0 from above. And 0 is x, of course, tends to 0. So this is exactly the situation, 0 times minus infinity. And that can be easily turned into a L'Hopital application by a simple reformulation. So this is the same limit as, we'll just leave that ln as it is. And instead of multiplying by x, we divide by 1 over x. And of course, that is the very same situation here. But what has changed now is that the numerator, again, that goes to minus infinity. The denominator now goes to plus infinity. So we have a infinity over infinity situation. And remember that we can just factor out a minus here, so we can turn this into infinity over infinity, or minus infinity over minus infinity. So that does not really matter. We can apply L'Hopital's rule now. So, and if we do that, you know, the derivative of the ln is 1 over x. The derivative of 1 over x is minus 1 over x squared. So what we get is the limit as x tends to 0. Let's see, we have this 1 over x times minus x squared. So effectively what we get is x tends to 0, the limit of minus x. And of course that can easily be seen to be 0. So this solves the situation here. Again, the simple reformulation leads to something that we can apply L'Hopital's rule to. Part C, and also part D that will be similar, is a limit of the kind 0 to the power of 0. And again, it's not clear what that is. Basically, it boils down to, well, if the base or the exponent is faster than going to 0. And of course, they may also cancel out somewhere in between. So that's something entirely different comes out here. As an example, we'll have a look at x to 0. A very simplest expression of that kind is x to the power of x. And if you have something like that here, so we have 0 here, 0 here in the limit, it usually pays to reformulate that as a limit of an exponential, a traditional exponential function, so e to the something. And if you want to express a power like this as e to the something, what you can of course do is simply express this as e to the power of ln x to the power of x. Same thing, yeah? E and ln are inverse to each other, so those basically cancel out. This is useful still because we can now apply the rules of logarithmic computations. And the ln of something to the power of something is the same thing as taking this power here and putting it in front of the logarithm. So this is the same thing as e to the power of x times ln x. And now one more thing. The exponential function is a continuous function. And that means this limit here is the same thing as taking the limit of the exponent and then applying the exponential function to that. So this is true because the exponential function is continuous. We can write this as e to the limit as x tends to 0 of x ln x. And this is a limit that we know from before, remember? We've just computed that here, the limit of x ln x, and the result was 0. So from B, we know that limit. So this tends to e to the power of 0, and this is 1. Okay, and finally, two different examples of that type. Let's start with infinity to the power of 0. And of course, we'll also have 0 to the power of infinity. That's going to be the next type. And this example here is x tends to infinity. And again, we make it very simple. We use x to the power of 1 over x. So basically, x tends to infinity, 1 over x tends to 0. So we have exactly that situation, infinity to the power of 0. What is that limit here? And again, that is a situation where we can apply L'Hopital's rule. And again, we use this reformulation by saying, well, this is e to the power of ln of this here. So let me write that out once more. E to the power of ln of x to the power of 1 over x, like this. And that in turn is equal to e to the power of 1 over x ln x. And again, as the exponential function is continuous, we can write this as e to the limit as x tends to infinity of ln x over x. So all we need to do is compute that limit. So let's do that. So we need the limit of ln x over x as x tends to infinity. And here we are again in a situation where ln tends to infinity and x tends to infinity. So that's infinity divided by infinity. Both functions are easily differentiable. So that's an application of L'Hopital's rule here. And what we do is we differentiate ln x, that's 1 over x. We differentiate x, that's just 1. And now the limit of 1 over x over 1 for x to infinity is, of course, 0. And that means what we get for our original limit, remember we started with x to the power of 1 over x as x tends to infinity. We reformulated that to read e to the limit of x to infinity ln x over x. So that is now e to the power of 0, and that again is 1. Specifically, just as a quick note, x to the power of 1 over x. So if x is an integer, we have something like n to the power of 1 over n, and that can also be written as n to the power of 1 over n. That can also be written as the nth root of n. And what our finding here implies that for n to infinity, this converges to 1. So incidentally, we've also shown the limit of that sequence here. So one more example, one last example for this video here. Of course, we'd also like to have a look at a type 0 to the power of infinity limit. And again, we choose the simplest possible case here. So we take 1 over x to the power of x now and let x tend to infinity. And of course that means 1 over x tends to 0, x tends to infinity, so we have exactly that kind here. And we can solve that in almost the same way as above. So what you get here is we again formulate that by taking the limit of e to the ln of this expression here, and then we take this x in front of the ln. So what we get is e to the power of x ln 1 over x. And again, as e is continuous, we can just write this as e to the limit of x times ln 1 over x. X tends to infinity. And now one last trick here to be able to apply something that we know already. A little reformulation to that ln. We can, instead of ln 1 over x, we can also write ln x to the power of minus 1. 1 over x is x to the power of minus 1. And then we can again apply the rule of logarithms. We can take this minus 1 out of the ln. And that means what we can write here is e to the power of minus, so we take that all the way out, minus the limit of x ln x. And as you know, x ln x, that's something that we don't really have to look at in this case. As x goes to infinity, of course, ln also goes to infinity, so that product will certainly go to infinity. And that means we have an expression of a form e to the power of minus infinity, and that will simply go to 0. So you'll notice we did not even use L'Hopital's rule in this case. All we needed was the computational rules of the logarithm and the e function, but it was just such a nice fit that I wanted to include it here. Okay, that concludes our little series of examples on the application of L'Hopital's rule. As usual, you'll find more examples on the exercise sheets. And in the following videos, we're going to go a little deeper into the idea of approximating a function through its derivative, or maybe through higher order derivatives as well. So we'll expand on that a little bit. And as usual, I hope I'll see you then.